Hi class. In today's video we're going to be talking about section 5.4, graphs of the sine and cosine functions. And so remember back when we started talking about our Cartesian coordinate plane and graphs, we used our ordered pair x comma y. And x always referred to our input and y referred to our output. And these we also called our independent and dependent variables, right? Because x could be whatever we wanted, and then y would be a specified output for each particular x. And so we could say, well, y equals, say, sine of theta, or y equals cosine of theta. So that for a given theta, we'll have a corresponding y value. And so it's probably easier if we remember our unit circle from last time. And we'll go ahead and start with sine. And remember our sine was our y value of each of these points. So sine of 0 is 0. And to make our life a little bit easier, I made a table. So sine of 0 is 0. Sine of pi over 6 is 1/2. Sine of pi over 4 is 1 over root 2. Root 3 over 2. 1. And so I'm just going to copy these as I go around the unit circle. Root 3 over 2. 1 over root 2. 1 over 2. 0. Negative 1 over 2, negative 1 over root 2, negative root 3 over 2, negative 1, negative root 3 over 2, negative 1 over root 2, negative 1 over 2, and we're back at 0 at 2 pi. And so what happens if we call this our thetas, our x, and our output y, and we graph these on a graph? Well, I have this nice coordinate plane. It goes from 1 to -1, and then these demarcations are pi over 12s because that gives us our pi over 6, pi over 4, and pi over 3. So here at 0, we said sine was 0. At pi over 6, we said it was 1/2. So pi over 6, we're at 1/2. At pi over 4, we're at 0.7. So 5, 6, 7. So somewhere like that. Pi over 3, we're at 0.866. So 7, 8. Up here at pi over 2, we're all the way up at 1, and then we just start to fall back down on that same pattern. 0.866, 0.707, 0.5, and then at pi we're back at 0. And now we could keep marching along this way, but because of where I put my plane, I'm going to graph the negative ones. So remember here, 11 pi over 6 is coterminal with negative pi over 6. And so what I'm going to do is I'm going to go ahead and graph the negative side. So negative pi over 6, we're at negative 1/2. Negative pi over 4, we're at negative 0.7. Negative pi over 3, we're at negative 0.866. At negative pi over 2, we're down at negative 1. And then we follow our pattern back. Oh, that needs to go over 1. So that one's there. That one's there. That one's there. And at negative pi, we are at 0. And so ignoring that one error point, if we connect this curve, we get y equals sine of theta. And this is what our graph looks like. And now we have quite a few characteristics that we define based on this graph. And so remember I said I could have kept going, and this curve here would have been over here, right? And so we would have had another swoop down. Here we could keep going left and another swoop up, and it will repeat if we continued further to the right or left. So this width from negative pi to pi, or 0 to 2 pi, is called the period. And for sine, the period is 2 pi, because this piece will repeat infinitely to the right and infinitely to the left because we have coterminal angles. We also talk about the maximum height of our graph. So this is M, the capital M, max height, or value. The maximum value here is 1. Or over here we have the minimum value. Right, so it's something like that. And we define this maximum distance between the peak and the valley. This is called the amplitude. Capital M minus little m is our amplitude. But it's not just this distance, because amplitude is really half of this value by definition. So this is not the amplitude. This is the range. The amplitude is half of that distance. And so what does that look like on this picture? Well, that's the distance from here down, or from here up. And so capital M minus little m by itself just gives us our total range, but half of that distance is the definition of amplitude. So we have a maximum value with capital M, a minimum value of little m. We can define its range, which is 2 in this case, right? It's 1 minus negative 1, which is 2. But its amplitude is half of 1 minus negative 1, which is half of 2, or 1. Now let's go ahead and graph this on our graphing calculator. So as long as you are in radian mode, which it'll tell you here at the top, and we graph y equals sine of x. If you go to zoom, and zoom 7 is called zoom trig, because we're looking at our trigonometric functions. It's going to give you a nice space that shows you your trig functions hitting at nice, neat points. Each of these tick marks is a pi over 2. So that first one's pi over 2, we're up at 1. And then at pi, we're at 0. And continuing along, 3 pi over 2, we're at negative 1, which we knew from here. And 2 pi, we're back at 0. And so this gives us our nice, neat graph on our graphing calculator. But let's go ahead and we'll graph our cosine function by hand. I'll get my table back. and our unit circle. And so now we're just going to read our x coordinates for our cosine values. So at 0, we're at 1, root 3 over 2, 1 over root 2, 1 over 2, and then 0, negative 1 over 2, negative 1 over root 2, negative root 3 over 2, negative 1, negative root 3 over 2, negative 1 over root 2, negative 1 over 2, 0, 1 over 2, 1 over root 2, root 3 over 2, and back at 1, right? Because it's periodic, we should end where we start. And then if we want to go ahead and graph these points, so now at 0, we're up at 1. At pi over 6, we're at 0.8. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 0.866, 0.707, 0.5. Pi over 2, we're at 0. 2 pi over 3, we're at 1, 2, 3, 4, 5. Negative 0.5. Negative 0.7. Negative 0.86. And at pi, we're at 6, 7, 8, 9, 1. Negative 1. So it looks like that from 0 to pi. And again, I'm going to go to negative pi to make our life a little bit easier. So here at negative pi over 6, we are at 0.866, 0.707, 0.5, then at negative pi over 2, we're at 0. Our pattern continues, negative 2 pi over 3, we're at negative 0.5, negative 0.707, negative 0.866, and at negative pi, we're back down at negative 1. So if I connect these points, is something that looks like this. And just to go over all of our features again, this height is our m, this height is our little m, negative 1 and 1. So amplitude is 1/2 m minus m, 1/2 1 minus negative 1 is 1. The period is also 2 pi, because this would repeat infinitely in both directions. And if we want to graph those together, right, you can start to see how that would look, but we'll use our graphing calculator for that. So if we have y equals sine x in our first, y equals cosine x in our second, and we hit graph, we see something that looks like this. Now, what do you notice? They look an awful lot alike, right? They're just shifted a little bit. And we have our typical transformations. So transformations. Remember, we have our H, S, R, V, help students remember variables. We have our horizontal. We have our stretch and shrink. We We have our reflections. And we have our vertical shifts. And so it looks like each of these points of, say, our cosine function is just our sine functions shifted left pi over 2. So if we look at this, sine of theta, and if we want it to shift left, remember we add pi over 2. So if we would shift each of these over 1, what happens? Sine of pi over 2 plus x well, where's our line? I'm going to make it a thicker line so that we can see it. So here's our sine. Here's our cosine. And where's that black line? Sine of theta plus pi over 2 is cosine of theta. And so notice what's happening is the same as something we learned in 5.2, where we had our cofunction identities, where our sines and cosines were just offset by pi over 2. So our horizontal shifts are our typical sine of x plus or minus some constant value, or our cosine x plus or minus some constant. And whether that's x or theta, it doesn't matter. But our horizontal shifts work exactly how we would expect. Now, if we want to talk about stretches and shrinks, this is where we have the possibility of some constant times sine of theta, or some constant times cosine of theta. Well, if we look here at our sine function, if we would look at y equals half sine theta, well, this point at pi over 2, 1 would become pi over 2, 0, or a half, rather. And this negative 1 would become negative a half. And now we would end up with something that looks like this. And so instead of doing some cosines, let's look at 2 sine x and half sine x. So we have our base function sine x. We have our 2 sine x, so notice it becomes twice as tall. Or our half sine x, which is half as tall. And so our stretches work exactly like we expect. But what about the cases? So this is changes the amplitude. But what if we have something that looks like a theta, or cosine of a theta? So if we have sine x, then we have sine of 2x, or sine of half x. So we have sine x like we expect. But now what's happening? In that 2x and that half x, so what we see is a constant times our function changes the amplitude. And this is our vertical stretch or shrink. When we have our multiplicand inside, this changes the period. And this is our horizontal stretch or shrink. Because what happens if we have, let me get rid of just one of those and it's going to redraw it, is if we have 2x, how long now does it take us to repeat? Well, before, and so we can look, say from this peak, or this valley to this valley, or this 0 to this 0, the entire cycle, the entire period happens in pi now. So if we have, and let me get a new piece of paper, if we have sine of theta versus sine of 2 theta, here the period is 2 pi, but now the period is just pi. Or if we have sine of theta versus sine of a half theta, our period went from, I don't know, I was going to write a theta for some reason, 2 pi to, it's going to redraw our friend, sine of x. And so now it takes from, so we have a peak to a peak. So what we did here is we divided our period by our coefficient. So our period is now, because 2 pi divided by 2 give us pi. 2 pi divided by a half gives us 4 pi. And so whenever we have our stretch or shrink outside our function, it changes the amplitude, and it's a vertical stretch or shrink. Whenever we have our stretch or shrink inside the function in front of our theta, that changes the period and it becomes a horizontal stretch or shrink. Reflections work as we expect. So this is still just negative sine x or sine of negative x. So we have this is about the x-axis, and this is about the y. So for example, if we have sine of x, negative sine of x, and sine of negative x, we have our friend sine of x, which we're going to get real tired of looking at soon. Negative sine of x, right? All those positive ones become negative ones. And then we see an interesting phenomenon because it's symmetric about the origin. This gives us the same value. Vertical shifts, those work as expected too. So if we have sine of x plus some constant, or cosine of x plus some constant, or minus some constant, it's just going to shift it up or down. So here we have sine of x plus 2. So we have our sine of x. Sine of x plus 2 just moves the whole thing up. Notice the amplitude is still 2 because the distance from the peak in the valley, or the amplitude rather, is 1, because the distance from the peak and valley doesn't change. It's just now centered around a different point. And that was a lot of time spent on two functions, but they're really important functions because next we're going to be talking about the graphs of the tangent function and then all of our other reciprocal functions. So I won't be going through the same process of writing all of these out by hand with a table, but I thought it was important that we saw the connection between the unit circle, our table of values, and our graph. And so I think keep that in mind, but for the most part, you should be able to describe what's going to happen in terms of transformation, but I want you to be able to graph them either on a graphing calculator or if you use GeoGebra. These all work exactly the same. Have a great day, everybody.